Hello dear friends, welcome to this introductory session on ARM Cortex-L3 LPC1768. ARM is abbreviated as Advanced Risk Machine. It is a joint venture of Apple Computer, Acron Computer Groups and VLSI Technology. Over a period of time, ARM has continued developing new processors and system blocks. And the few popular ones are ARM7. And presently, the portfolio has emphasized more on the development of the CPU, which has resulted in the architecture version 7. In this particular version, the architecture is designed and it's been divided into three profiles. It is A profile, R profile, and M profile, which is being said as ARM Cortex A, ARM Cortex R, and ARM Cortex-M. What is the A profile? It's being designed for high performance open application platforms. Then the R profile is designed for high-end embedded systems in which real-time performance is needed. And the M profile is designed mainly for the embedded microcontroller based systems. So in this session, we will be talking more about the ARM Cortex M3, that is LPC1768. So the session would be cover the features of LPC1768, the block representation, and few glimpse about the pin configuration. The features of LPC1768 goes, as said, it is the ARM Cortex M3 series. That means LPC1768 can be used for all the microcontroller or controller based applications. It is a 32-bit RISC based processor. RISC stands for Reduced Instruction Set Computer, and it is a 32-bit. What we mean by 32-bit is the internal processor, the ALU, performs operations up to 32-bit in a given clock cycle, which also implies that all the registers are of 32-bit. The data bus is of 32-bit. Being a 32-bit processor, it can also perform 16-bit as well as the 8-bit. But the utility of this controller would be more appropriate for the applications which are of 32-bit wide. RISC processor, the features of the RISC have been embedded into LPC1768. That is, each and every instruction is encoded uniformly, which is 32-bit again. The clock cycles required for the instructions are uniform. The number of addressing modes that are used are less in number. It has got a large number of internal or the CPU registers, and the architecture is based on the load and store, wherein the data to be obtained from the memory or into the memory specifically uses the instruction load and store. The next important feature is it has a 3-stage instruction pipeline and the Harvard based architecture. Pipelining is a technique, or it is a concept which helps in utilizing the internal blocks or the functional blocks more efficiently. And moreover, when you say it is an instruction pipeline, we know that an instruction consists of 3 stages mainly. The first instruction is being fetched, it is decoded and executed. Now these 3 stages are pipelined, which implies when the instruction 1, let's take example, is in the phase of fetching, the instruction is being fetched and then it's sent for decoding. So the fetching unit is fairly free enough. So the next instruction, that is I2, can be fetched. So if you look from the clock cycle perspective, in the first clock, the first instruction is fetched. In the second clock, the first instruction enters into the decoding stage while the second instruction enters into the fetch stage. So are we not doing the more, you can say more operations in a given clock cycle. Yes, that's what we say to be as pipelining. So the support of the pipelining is there in case of LPC1768, and it is a three-stage pipeline. The next feature is the Harvard-based architecture. Now, the architecture of any controller or a processor is based on different parameters. As in the previous point, we said the RISC, you have the controllers which are even designed using the CISC processor, CISC based. Similarly, the memory arrangement defines the type of the architecture. So if at all you have a memory of the processor which is combined, that means the code and the data goes into one set of the memory itself, right? There is no demarcation saying that the code memory is used only for storing the instructions, the data memory is only for data. Then that type of architecture, that is a combined memory architecture, we call it to be as the von Neumann. In case of the Harvard architecture, you have a separate memory for the code and a separate memory for the data. The advantage here is the speed. Fine. And LPC1768 has the Harvard based architecture wherein there is a separate memory for the code and the separate memory for the data. The next feature we have is the ARM CortexM3 operates up to a frequency of 100 megahertz. That's the speed at which it operates upon. Coming to the memory, it has got a memory of 512 on-chip flash. Now, what is the use of this flash memory? The flash memory helps in the speeding up of the performance. That means it accelerates the maximum performance for the use. Use with different bus architectures that are supported with the LPC1768 and ARM Cortex. It's being used for both the code as well as the data storage. The programming of this flash memory, it can be accomplished in several ways. It may be programmed with in-system programming via the serial port, and that's what we have with the LPC1768. And the application program may also erase, it can be erased, it can be programmed while the application is running, which allows a great degree of flexibility for data storage field firmware upgradations. Then LPC1768 also supports up to 64 kilobytes of on-chip RAM. So this on-chip RAM is used, right, for storing the data into this particular memory. Up to 32 KB of the SRAM is accessible by the CPU, and all the remaining, that is the remaining part, DMA, that is the direct memory access controllers, which are on the higher speed bus, utilize it. The devices containing more than 32 KB SRAM have additional 16 KB of the SRAM block, and each are situated in a separate slave ports of the advanced high performance buses. The architecture here allows for the CPU and the DMA to be accessed separately such that few or no delays occur in the bus mastering. It has got 8-channel DMA controller. DMA stands for Direct Memory Access. Now, what's the use of DMA, or what is the functionality of the DMA? Whenever there is the operation, right, or the processor is not required to be a part of the execution process, then the question arises, why unnecessarily waste the CPU time? For example, as seen here, when it is ADC converting analog data into digital, it's the functionality of the ADC block. Similarly, converting digital to analog is the block, functionality of the digital, DAC block, wherein the processor is not really required. But nevertheless, ADC requires some data to be accessed from the memory, sent to the memory, and so on. The controller gives the authority to the DMA controller or transfers the control to the DMA controller during these operations. That's the job of the DMA controller, mainly whenever the operations are related with the memory wherein the processor is not really required. This looks pretty complex, the block diagram of LPC1768, but it's a very simple way to understand it. Let's look at each of the blocks of LPC1768. The heart of LPC1768 is the ARM core. ARM company, right, or ARM does not give the silicon chip. Fine, they do not manufacture the chip. The ICs, whatever we get of the ARM, is not from ARM. What are they providing is just the soft core. The core processor, which consists of the test debugging interface, or it could also be the core CPU that I'm talking about, right? The processor, the system bus, fine. All that is only being provided by ARM in the soft. That means the RTL code, to be very specific about, is being provided by the ARM core. Right, and while the other companies, the silicon-based companies or the controller-based companies develop different peripherals around this ARM processor, and they are out into the market as the chip. Like for example, we have here LPC1768, which is of the Philips made. Similarly, we have got analog devices, we have got STM and so on, which have their own 32-bit ARM controllers processors. The next block we have is the DMA controller, as discussed already, direct memory access controller, which is being used as an alternative for the ARM whenever there is a memory related operation. The next block that we have is the clock generator. So the clock generator is responsible for generating the clock for all the internal blocks, the peripherals, the processor, fine, and as well as for the GPIOs and so on. The clock generator generates a different speed of the clock because the processor works at a very high speed while the peripherals are working with a low speed. The next block we have is the ADC. ADC stands for analog to digital converter. It's a 12-bit ADC which uses internally as the successive approximation technique with 8 channels and the support of the DMA. The next is the D2A converter. All these can be seen over here. This is what we have is the DAC. Here is the ADC, right? Then this particular block has got, or rather it generates a variable analog output. It's a 10-bit DAC which accepts 10-bit of the digital data and converts into the analog equivalent. The maximum output value of the DAC is dependent upon what is the V reference voltage that's being obtained. And the ARM works with a very low voltage of 3.3 volts, unlike other controllers which operate at the 5 volts. So we could see that the maximum analog input that goes is again a 3.3 volts. Similarly, the maximum analog output that we get will be about 3.3 volts. The next internal, these are all on-chip peripherals, okay? Whatever we are discussing are the on-chip peripherals. The next one we have is the timer and the counter. So this is a 32-bit general purpose timer and the event or external event counter. LPC1768 supports four such 32-bit timers and the counters. As you can see over here, capture, compare, timer 2, 3. Fine. Similarly, you have got here capture, compare, timer 0 and 1. Right. This is a block of the timer and a counter. So the timer counter is mainly designated to count the cycles of the system, right, which is being derived from the clock, or it could be the externally supplied clock. So it can optimally generate interrupts, it can generate timed DMA requests, or perform other functions at specific time values. Based on the four, or as we saw here, the capture, compare, timer registers, all these operations are being performed. Then each timer counter also includes the capture input or the trap timer value. When an input signal transitions occur optimally, it generates an interrupt. The next block is the UART, which is the Serial Communication Interface. UART stands for Universal Asynchronous Receiver and the Transmitter. So serially, any data that has to be transmitted or received can be done using the UART. Fine. Now, the UART are two in number for LPC1768, and in addition to the standard transmission and reception of the data lines of the internal CPU, UART also provides a full modern control handshaking interface because it's asynchronous. So there are handshaking signals that take place between the transmitter and the receiver. And it supports the RS protocol, that is 489, which has got the 9-bit mode allowing both software address detection and atomic address detection using this 9-bit mode. And the standard baud rate that's being used is your 115200 is the baud rate. What is baud rate? It is the rate at which the data is being transmitted. It's basically bits per second. The serial interface is also supported by the SPI, serial control. So this SPI, that is the serial peripheral interface, is a full duplex serial interface which is being designed to handle multiple masters and the slaves connected to a given bus. Only a single master and single slave can communicate on the interface during a given data transfer. And during a data transfer, the master always sends 8-bit to 16-bit of the data to the slave, and slave always sends 8-bit and 16-bit data to the master. The next we have is the I2C, which is inter communication. Again, it's a serial bus interface support, and each of these LPC1768 has 3, as you can see here. I2, this is 1 minute 1. Yeah, SPI, then you can see these are the small blocks. Yeah, I2C you have, right? Fine, you can see the blocks, the details can be obtained upon. Wherein it's a bidirectional for inter IC controls, which uses only 2 wires, right? It's the serial clock line and the serial data line. So each device is being recognized by a unique address and can operate at either receiver only device, or it can be transmitter with a capability for both reception as well as the transmission of the information. And I2C is a multi-master bus and can be controlled by more than one bus controller which is connected to it. The next block is the PWM, that is pulse width modulator. This pulse width modulator is based on the standard timer block, and it inherits all its features, right? Although only the PWM function is used in LPC1768. This timer is being designed to count the cycles of systems derived from the system clock and optimally switch pins generate interrupt to form or rather to perform other actions. When specified, timer value occurs based on the 7 match resistors. The function is in addition to the features of the timer and so on. And moreover, it's based on the match resistor event. The main application of using this PWM is to control the what you can say the speed of the DC motor, wherein by varying the duty cycle of the PWM, you can go in the varying the speed of the DC motor. The next block is the Watchdog timer. The purpose of this Watchdog timer is to reset the microcontroller within a reasonable amount of time if it enters in an erroneous state. Right? What is Watchdog? What is the function of or what is the dog doing at a house? If you have a pet at home, it keeps watching, right? If something goes wrong to the or somebody comes, then it starts barking, right? So is the functionality of the Watchdog timer in LPC1768. Whenever there is an error, right, then this Watchdog timer resets and it pops up. When enabled, the Watchdog timer will generate a system reset if the user program fails to feed or reload the Watchdog within a predefined amount of time. So having discussed about the internal blocks of LPC1768, let us quickly look at the pin configuration or the pinout of LPC1768. LPC1768 is a 100 pin IC, of which you have 70 pins forming the GPIO. What is this GPIO standing for? It is the general purpose input output, right? And all the operations that happen will be through this GPIO. The GPIO of LPC1768 is the fast general purpose parallel input output. The device pin that are not connected to the specific peripheral functions are controlled by the GPIO resistors. These pins may be dynamically configured as inputs or outputs. Then separate resistors allow setting or clearing of any number of outputs simultaneously. The value of the output resistor may be read back as well as the current status of the port pins. The important feature of the GPIO is it provides more than one functionality. Unlike the lower controllers, which are just 8-bit and so on, they are very specific to one functional. As you can see, to one pin, you have got so many color codes added over here, right? So each color code that you can see indicates one function. So if it has got 3 color codes, that means it supports 3 functionalities. If it has got 4 functionalities. If it has got 1, it's only one function. So LPC1768 GPIO supports maximum up to maximum up to 4 functions at a given time. It is a normal GPIO as a simple input output. Then you have first alternative, second and third. And the whole of the programming of this GPIO is managed with the pin select resistors and the GPIO resistors. The details of the GPIO resistors are discussed in my next slide, in the next lecture of GPIO resistors. So quickly we'll summarize on the session what we discussed. We learnt about the features of LPC1768, the internal block diagram, and we have quickly glimpsed upon the functional blocks of LPC1768 and their fundamental or the basic functions. And then we have seen the pinout of LPC1768. So thank you for watching this video. Request you to like, share and subscribe the channel to get more inputs on the LPC1768, its programming of the GPIOs, programming the internal peripherals. Thank you.